It is a great pleasure to have David Ben-Zvi as our first speaker in this new seminar, which is the SMRI Algebra and Geometry Online seminar. He'll be talking about boundary conditions and Hamiltonian actions in geometric Langlands. And if you would like to see more of this, he gave two very nice talks earlier this year at MSRI. And perhaps we can begin with one story about David. So he's a luminary in our field. I remember some years ago, I was at a conference in Corsica, and there was a kind of sandbar off the coast. And David liked to swim out there and kind of stand on the sandbar. And basically people would swim out to the sandbar and ask a mathematical question and then swim back. And Ian Gordon joked that it was everyone swimming out to consult the oracle on the sandbar. Thank you very much, David.
Well, thanks a lot, Jordi and Emily, for the invitation. It's great to be in Sydney. I have a fairly loose agenda of what I'd like to cover today. So I'm very eager to answer questions as they come up, or during the break or at the end. So please let me know. So what I'd like to tell you something that kind of is related to my joint work in progress with Yanis Sikalaridis and Akshay Venkatesh. So any kind of new content is going to be joint with them, though a lot of what I want to tell you is not going to be new content. Just want to tell you about some field theoretic structures, some structures inspired by quantum field theory in the geometric Langlands correspondence, and how they lead to in particular, the Langlands duality and Hamiltonian actions for reductive groups, which is the topic of our work. So I wanted to mention while we're here some of the key references. If I don't get to them later, there's the derived geometric satake of Bezrukavnikov-Finkelberg will be kind of the main technical tool I'll use, and the construction of Coulomb branches by Braverman, Finkelberg, Nakajima is very closely related to the kind of ideas that I'll be explaining. The duality of Hamiltonian actions is inspired by work of Gallardo and Witten, and this mathematical implications of Gallardo and Witten are being explored in work of Justin Hilbert and Phil Sangue. Okay, so what I'd like to explain, as I said, is something about the field theoretic structures in geometric Langlands. So the very coarse way I want to think about the geometric Langlands program, I have a G is going to be reductive group, and we might as well think about G as being GLN, and G dual will be the Langlands dual group, which in that case will again be GLN. Most of the time I'm going to work over the complex numbers, but in general I'm going to work over an algebraically closed field. So some of the motivation for saying things in the kind of algebra geometric way that I'll emphasize them is in order to work in characteristic P. So that's sort of one reason we're going to say some things in particular ways, but can think of everything as being about C today. So the way after kind of Kapustin-Witten kind of taught us how to think about the geometric Langlands correspondence as an equivalence of two four-dimensional topological field theories, which I'm going to call kind of A sub G and B sub G check. So I'll call this the automorphic side and this the spectral side. So we think of having these objects are roughly, so in the physics world, there's going to have the structures of four-dimensional topological quantum field theories. And a lot of the structures that we know and love in the Langlands correspondence in general can be fit into this framework. And that's kind of the kind of theme I want to make sense of. In particular, so what's on the B side, the B theory, you can really make sense as an extended four-dimensional topological quantum field theory, at least in certain settings in what's called the Betty setting. There are various versions of these things in various contexts that we can flit between. So the B side really can be made sense of in a kind of language of topological field theory. And what this does is, given a manifold, we're going to attach to it some invariant, which is a linearization of the space, the character variety, if you like, the space of G-check local systems on M. So these are, if you like, representations of fundamental group of M into this complex dual group. So I'll say more specific things as we go along. But the B side, at least the background geometry is somewhat clear. You start with a manifold of dimension up to 4, and you look at the space of representations of its fundamental group into the dual group, and you linearize that. So the A side, is much less clear, is much more complicated. In the geometric Langlands correspondence, this is what has to do with moduli spaces of G bundles on algebraic curves. So here, C for me will always be a smooth projective algebraic curve, or maybe if you like a compact Riemann surface. And again, I'm working over an algebraically closed field. But this is a lot harder to make sense of in the full structure of four-dimensional quantum field theory. So we have little bits and pieces of it. And that's what I guess I want to spend a lot of the talk talking about, is like what parts of field theoretic structures can we already see on this A side and be inspired by what we see on the B side. So really what we're going to make sense of, and the entire talk will only focus on the kind of 1 and 2 dimensional part of the field theory. So we're talking about a 4-dimensional field theory, so it attaches invariance theoretically to manifold dimension up to 4 to a surface. It's going to attach a category. And so here, as the role of a surface, I'm going to take my curve C. So algebraic curve C will play the role of a surface. For the role of a circle, I'm going to take a punctured disk. So spec of field of Laurent series in one variable. So that's going to play the role of a circle. So the kind of pictures we're going to be talking about are these kind of pictures where I have that's a terrible algebraic curve, but there it is. So I'm going to talk about algebraic curves with marked points. That's going to be the geometry for which we know how to make sense of on the A side, but we're still going to try to extract out of it as much field theoretic structure as we can. And we're going to try to say it in kind of algebra geometric language in order so that this makes sense, for example, in characteristic P. Okay, so what I'd like to focus on today is I wanted to talk about 2 ideas from topological field theory that I want to emphasize and how they appear in the Langlands correspondence. And the main one is the idea of a boundary theory, or boundary condition, they're often called, for a topological field theory. So what is a boundary theory? And I'll try to say some more precise things later. What I want to think of a boundary theory for, let's say I have a TFT here. In my case, I'm interested in 4-dimensional TFTs in the Langlands program. So a boundary field theory is going to be roughly a 3-dimensional field theory. So a boundary theory is roughly a theory of 1 dimension lower, but somehow it's not, in general, should not be thought of as a decoupled thing that has its own life. It's something that lives on the boundary. So I don't know. So just think of having I have kind of a bulk where my 4-dimensional theory lives, and on the boundary I'll have something that this is going to be my boundary theory. So it's something that makes sense on the boundary where there's kind of a bulk material, which is given by Z. So so another one way to make this kind of, if you like the functorial formalism of topological field theory, if you like to think of topological field theory as a functor out of some cobordism category, what a boundary theory is we're going to extend the functor that's out of a cobordism category. We're going to extend it to a category of manifolds where we have with a marked boundary component. Marked boundary, and this marked boundary is going to be marked by my boundary theory. So it's going to be something I'm going to attach. I'm going to attach invariance now. I do everything that I used to do in the field theory, but now I also have a boundary component that's labeled by the boundary condition. So you can make the axiomatics of this. This is covered, if you like, by the kind of cobordism hypothesis with singularities of Lurie, that kind of formalism. But we're going to think about it. This talk, by the way, big caveat, is going to be extremely informal. I could try to say some things more formally as people ask, but this is just to warn you now. Okay, so this is the main kind of idea, and what the kind of caricature that I wanted to explain, this is what appears in my work with Sakalaridis and Venkatesh. We want to think about the geometric Langlands correspondence as having not just an equivalence of 4D field theories, but it's also going to be a field theory. I'm going to have a boundary condition. Let me just write it as an element. This is, think of this. There's going to be a boundary condition I'll call P sub x, P for period, and we're going to try to match boundary conditions on one side with boundary conditions on the other side, L for L functions. So that is that extend the geometric Langlands correspondence in the presence of boundaries. And that's sort of what I'd like to explain today. The other structure that I want to use, so the way we're going to try to extract, so the idea is that you can extract algebraic geometry. You can extract some geometry out of the abstract structure of a field theory. So a field theory might be given to you in some geometric way, but by the way it's constructed. But I want to kind of take there's an intrinsic way to take a topological field theory and attach to it some algebra geometric object, which I like to think of as the spectrum of the field theory of Z. This is a version of what, let me call it M sub Z. This is a version of what physicists call the moduli space of vacuum. Or just let me call it just the moduli space of Z. This is the moduli space of vacuum of Z. And so roughly what I'll think about this, the various variants of this, I'm going to take this as a spectrum. It's really going to be an object of algebraic geometry. It's spectrum of an algebra. So out of the field theory, I'll construct an algebra, either algebra of local operators or more generally algebra of defects. We're going to construct defects in the field theory Z of various dimensions. And you can use these to construct a space. And this is kind of the algebraic geometric content of the field theory. So the idea is that the idea is that the theory Z will, in some universal way, kind of sheafifies or lives over or spectrally decomposes over this moduli space. And it's kind of a universal space over which it decomposes. This is very much, people in representation theory know this idea, taking the center of an algebra and taking the spectrum of the center as the space of natural kind of intrinsic parameters in representation theory. And then conversely, we can get Z can be recovered in some sense as a kind of geometric quantization of this moduli space. So geometric quantization is not really a functor, but it has the same relation. From the moduli space, we perform some kind of geometric quantization to recover the field theory. So that's somehow the kind of relation. Okay. So that's the kind of agenda. Now, here's a choice I make, and I seem to make the same choice in almost every talk I give. So if you've heard me, this will be very familiar. I like to kind of my comfort zone is to start with a kind of a toy model for topological field theory, which is I'm going to think about finite group, two-dimensional finite group field Yang-Mills theory, because it just sort of helps fix the ideas. So here this is going to be pretty far removed from the geometric Langlands correspondence, but I'll just start with G. G is now going to be a finite group. And out of it, you can construct, I don't know, with lack of notation, I'll call me Z sub G. It's going to be a two-dimensional topological field theory, which is, if you'd like, the G Yang-Mills theory or G Dycroft-Witten theory or whatever. But it's the basic gauge theory you can build out of a finite group. And there are not a lot of bells and whistles here. So what does this do? So what this does to a manifold M, so M, it's a 2D field theory, so M will be a manifold of dimension up to 2. This is going to be, it linearizes, or if you like, quantizes a space of fields, which is the space of G local systems on M. Now here, G is just a finite group, so G local system just means a G covering space, or G Galois cover, or if again, you'd like representation of the fundamental group into G. But everything is now going to be very discrete. So this is the space of G local systems. So what does the theory do? I'm not going to go into in great detail, but for example, if you have a closed surface, I'm going to attach to it a number. And that number will just be, I'm going to count the number of local systems on this surface. I have to count them with, or kind of do an orbifold count them with correct multiplicity. Given a one manifold, I guess I call it S1. Given a one manifold, I'm going to attach to it a vector space, and that vector space will be the functions. Here, everything is going to be for me complex valued functions on the same space of fields now on this manifold S. Okay, I look at G local systems on this space, and now I attach it the space of functions. This is a finite orbifold, so there's not a lot of ambiguity what functions means. And again, if I have a zero manifold, I'm now going to attach to it a category, which is, I guess I could call it complex valued sheaves on local systems, on G local systems on this manifold. Sheaves again here, and just now means vector bundles on it. We have a finite orbifold, and we're looking at vector bundles on it. So this is the kind of idea, and you could make this very easily into a structure of an extended field theory, and it's a very good kind of toy model for a lot of things in representation theory. But let me just
go
kind
back
of
one slide, BZ, for 2 seconds. I just missed the last
sure.
line.
Sorry, yeah. So I have a category attached to a zero manifold, which category of vector bundles on this space. So again, let me just point. Of course, there's only one zero manifold I care about, which is the point. And so to point, I look at vector bundles on. This is now point mod G. So I look at vector bundles on point mod G, and that's just the category of representations of G. Okay, so the basic object in this theory is the category of representations of the finite group. And this is also what appears, is that okay?
Okay. Good.
All right, so now what is a boundary? Let me, without writing too many of the axioms, what is a boundary theory for Z sub G? It's exactly a representation of G. So the basic objects we're going to study, these boundary theories are going to be representations. We take an object V in the category representations of G, if you like, which is again what my field theory attached to a point. And just to be concrete, the kind of for future reference, I want to think of representations as functions on a G space, maybe a finite G set. So I think of complex valued functions on G spaces as kind of the source of these boundary conditions. So in other words, if you'd like, what I'm doing is I'm doing quantum mechanics on this set X. If you'd like, it's topological quantum mechanics. Topological quantum mechanics is a very boring theory. There's no Hamiltonian. There's a finite dimensional Hilbert space, and that's it. There's just a finite dimensional vector space. Is basically all we have. So we think of this representation as an abstract vector space. You can think of that as quantum mechanics on this space X, or more abstractly, you just have a vector space. You can call it a Hilbert space if you want. And that's going to be our quantum mechanics. But what makes it a boundary theory? So here again, there's this picture that I'm thinking of. Here's a one manifold on which the quantum mechanics lives, but I'm thinking about it, this one manifold as being on the boundary of a two manifold on which you have this theory Z sub G. And that extra data saying that it's a boundary theory is exactly saying that this coupling to this G bulk is exactly saying it's a representation. So that's what the content of being a boundary theory is. Now you can say this more formally if you like. What is a boundary theory? It's a morphism. It's a morphism of two-dimensional topological field theories. I won't define that precisely, but you'll see it when you'll know it when you see it. It's a morphism of two-dimensional field theories from the trivial field theory to my theory Z sub G. So that's really how I can think of a boundary theory. A boundary theory is a morphism of field theories from the trivial theory to Z sub G. So what does that mean in practice? This means, so for example, if I evaluate this on the point, when I evaluate this on the point, the trivial theory, the category it attaches to the point is just the category of complex valued vector space. And so I need to give you a functor from this to what Z attaches to a point, which is representations of G. And such a functor is just given by where it takes the one-dimensional vector space, namely the representation V. So I want to think of this representation as a functor from vect to rep G. And the cobordism hypothesis philosophy tells you that once I've told you what happens on a point, everything else is determined. So the data of this boundary theory, you can think of it in various fancy ways, but at the end of the day, it's just given by an object of this category. An object, but I'm thinking again of an object as a functor from the unit category, which is vect, to my category. Okay. So that's what a boundary theory is. Now, just to illustrate a kind of thing that can do, so for example, if I look at this on S1, maybe I should do that on a separate page. So on a point, this just gave me the representation, but now I look on S1, and again, the trivial theory on S1 just gives me the trivial vector space, C, and I need to go to Z of S1. What is Z of S1? It's functions on G local systems on S1. G local systems on S1 is just conjugacy classes in the group. A local system is determined by its monodromy. That's all the local system on the circle is. It's just a monodromy. So it's a conjugacy class in the group. So these are just, if you like, class functions on the group. So in other words, given S1, I need to give you a map from C to class functions. In other words, an element of class functions, and that's just going to be the character of the representation. So that's what the boundary theory does on the circle. It's just give you the character. Okay. This is a probably completely unnecessary complication, but let me just say psychologically for me, it's always easier not to think of a boundary condition, but think of it as a special case of something slightly more general, which makes the kind of structure a little clearer, which is the notion of a domain wall. So domain wall, it's going to be a morphism of field theories. Domain wall is a physical name for what you might think of as a morphism between two field theories. So for example, suppose I have two groups, let me call them, say, G and Z and T, suggestively. So domain wall is going to be a map between these two theories. It's a map of field theories. What does that mean? That means that I'm going to extend so I'm going to be able to make evaluations not just for manifolds, but for kind of bipartite manifolds. I'm going to have manifolds which have kind of a blue half and a black half with a red boundary. So here so the T theory is what, so here I'm thinking of this as being T, the blue part. This as being the G theory. And the boundary is going to be given by, so this is what the data of the domain wall is giving. So it's an extension of the theory to kind of bipartite manifolds. So on one half I have T local systems, the other half I have G local systems. And if you think of T, for example, as a maximal torus of G and G, a finite Lie group, the natural thing to write here is, for example, look at B local systems on the boundary. So I have a Borel subgroup, so I have B, which has surjects onto T and sits inside of G. So that's kind of a nice example of a domain wall. So just the structure of domain wall feels to me a little clearer. You're taking of manifolds, and you're thinking about putting some defect in the middle. Since that might cut the manifold into two halves, you're allowed to do two different theories on the two halves. So in general, it's kind of just a functoriality of field theories. The special case of a boundary condition is just where on one half I put the trivial theory. So a boundary condition is just is a morphism from the trivial theory. But in general, you can use this to talk about functoriality between representations of different groups. Okay, does that make sense? Or I don't know if this helps or confuses things. This picture.
I'll ask a question.
Yeah.
So the functor that you had from vector spaces to rep G was obviously not a tensor functor. So, is that because you're talking about two-dimensional?
That's right. So yeah, so my categories here don't have, my category rep G is not appearing as a tensor category here. The structure that has to do with it being a two-dimensional field theory is just a C-linear category. So I guess I haven't specified, what world of categories I'm living in. So, it could have maybe abelian categories, C-linear abelian categories, or finitely co-complete categories, some version of finite categories, but there's no tensor structure here. And so the morphisms of field theories, so to define a two-dimensional field theory, I can give you any reasonable category. It doesn't have to have a tensor product. These ones happen to have ones, but my morphisms between them won't respect tensor vectors, won't respect tensor structures. Is that?
Yep, thanks.
Good. All right, so, okay, so that's just to give a sense of the kind of things a boundary theory is in the finite group case. Now, the other kind of structure I want to talk about, so I guess maybe just to go back to this picture, we have this picture of this is kind of a defect. A defect is some kind of singularity you can place inside of a theory. This is a kind of a codimension boundary, or a domain wall is an example of a codimension 1 defect, a singularity in codimension 1. The other kind of thing you can do is to do a local operator, which in 2D is the same as a codimension 2 defect. So I can think of what I can insert at the point. So let me think of here as being some one manifold and coming in, and some other one manifold coming out. And I'm going to think of a singularity that happens in codimension 2. So these are called local operators. So what does that mean? I take this little point and I kind of excise a little disk around it. And now I have a little circle here. So I have a bordism from S in union a circle to S out. And so that gives me a map on the axioms of field theory, gives me a map from Z of S1, tensor Z of S in. I'm being completely ignoring orientations and anything of that nature. But, or if you'd like, I want to think of this as Z of S1 gives me operators mapped to endomorphisms. Okay, my picture, let me think of this picture as being a S in cross an interval. Think of it as a product, so I just really get endomorphism of this Z of S. So this is the idea of a local operator, that elements of Z of the circle give me operators. I can insert and give me operators on the vector spaces attached to one manifolds. So these are called local operators. And again, Z of S1, we know what Z of S1 is in our theory. It's class functions. And we know that class functions has a ring structure. Class functions is the center of the group algebra. It has a structure of commutative ring. And where does that structure come from field theoretically? Field theoretically, let me just draw some pictures. I'm not really going to care about these manifolds on the outside. I'm just going to draw some small pictures. If I have a circle where I put a local operator and I have another circle where I put a local operator, I can think of it embedding them inside of a bigger circle. So I put some operator O1 here and some an operator O2 here, and then I look far away and I get another operator, which is O1, like call that the multiplication, the convolution of O1 and O2. So if you like, I'm just looking at this flattened version of the pair of pants. That's a cobordism from two circles to another circle, and it defines an operation on Z of S1. It's defined the binary operation. Let me already complicate this. The way I want to think about this is this structure that I can draw circles inside of other circles. This structure gives the vector space attached to a circle a structure of what's known as an E2 algebra. So it's an algebra over with a little two disks operad. That's what these pictures are. What that means in practice is, so I get chains on the configuration space of k points inside of a big disk, give k-array operations on my vector space attached to a circle. Now you say, where did chains come from all of a sudden? I mean, so depending on how I linearize these spaces, my vector spaces were all discrete. We're all, if you can think about it as chain complexes, but they're all concentrated in degree 0. If I had more general chain complexes, I'd see that this structure on the level of homology, this structure gives me two operations. There's multiplication, as I have two binary operations. There's a multiplication of degree 0, and there's a bracket of degree -1, which is kind of an odd, and together they form an odd Poisson algebra. So this guy is commutative, this guy satisfies a super Lie structure, and they satisfy some Poisson relation. So that's the structure you would have abstractly. In our case, Z of S1 was completely discrete, lived in degree 0. All I have is a single operation, which is now commutative. And so I found that this vector space of class functions has a commutative ring structure. But when we talk later in geometric Langlands, it's going to be important to keep track that commutative ring structure was actually happened. We got lucky somehow. There was potentially more structure. And if you looked in other 2D field theories, you'll see more interesting such odd Poisson brackets. Okay, but you can forget all that for now. The main point is that I have a commutative ring, the center of the group algebra. And we know in representation theory that everything in representation theory linearizes over to the center. And by Schur's lemma, every structure I have in representation theory kind of breaks down according to characters of the center, or breaks down over the spectrum of the center. So what I want to say is that this entire topological field theory kind of sheafifies or is linear over the center over this space Z of S1, which again is my class functions. So I want to think about that geometrically, is it lives over, let me define the moduli space of my theory, which is just spec of this ring. So I have this ring, it's a commutative ring, let's take its spec. Well, this is not something very unusual. You're taking the center of the group algebra or class functions. This is just the dual of our finite group, if you like, the unitary dual, the set of irreducible representations of G. So so the entire field theory breaks up according to irreducible representations. But I want to think about that geometrically as it's breaking up over this finite set, which is the spectrum of this ring. So what does it mean that the theory breaks up? That means, if you like, the number you attach to a two-manifold breaks up as a sum of contributions. The vector spaces break up as direct sum of vector spaces labeled by isotypic components. The category of representation breaks up as the categories of representations built out of different irreducible. And all the operations also break up. The whole field theory kind of decomposes over this space. Okay, so that's the kind of idea. Okay, so that's all I wanted to do from 2D field theory. So maybe I'd take a break for questions about this.
So how does the formula break up for the count of G bundles?
I should have, you're right, I don't have my notes with me, but you get a sum. The invariant of a closed surface is the sum over irreducible representations. I should really know.
Oh, is this Frobenius thing?
Yeah, it's this Frobenius thing, this mass formula. So it's something with the 2G minus 2 or whatever, some powers of the character. Okay, I'm sorry. I usually have this in my talks, I'm sorry, but I can't remember. But you get a formula for this that's not hard to derive just by cutting your surface up into pieces, and you can write everything in terms of characters. Mm-hmm. But so the fact that that number decomposes as a sum is kind of the number version of something. Later, there'll be something like an integral. And integral over this space of this moduli space. Okay. Okay. All right. So no more questions. All right.
Quick question, David.
Yeah. I can't actually see who's asking. But
sorry, Odette here.
Oh yeah, great.
Is there a slightly more sort of complicated toy model where we can actually see the E2 structure, like a non-trivial E2 structure?
Oh yeah, so the easiest example, I mean, basically you could take, the easiest example maybe is the B model. Well, I mean, you could take, to a point rather than I take any associative algebra. I can try to start defining a field theory where I attach my favorite category of representations of my favorite associative algebra. So to really get a full two-dimensional field theory, I maybe want this to be a smooth and proper DG algebra. But so for example, take the derived category of coherent sheaves on a smooth projective variety. You can write it as modules for some DG algebra. So that's my category. And the thing I'll attach to the circle will be, okay, then I have to be careful about orientations, but let's say it's a Calabi-Yau variety, then I have just the Hochschild cohomology of that algebra, which is identified the Hochschild cohomology. But the Hochschild cohomology, anyway, this is a long-winded way of saying Hochschild cohomology of any algebra, so that's the derived version of the center. Derived version of the center is not commutative, it's only E2. So this structure, this Gerstenhaber algebra structure, is exactly the structure that Hochschild cohomology has. So you don't see this if you're in the non-derived setting, because then to have a 2D field theory, you'll say you need a semi-simple finite dimensional Frobenius algebra. But in the derived setting, you don't need that. You can take any smooth projective variety, gives you this B model, and then you immediately get an interesting E2 algebra, and you could try to take its spectrum, some version of moduli space in the theory. Okay. Yeah, that's probably a better lead-in. I mean, that's much closer in spirit to what you see in geometric Langlands. Okay, so now let me talk. So now let's go to geometric Langlands, and I'll kind of fill in some of the structure of geometric Langlands as a field theory as we go on. But I really wanted to talk of what this picture of Guyot-Witten suggested for boundary conditions. And so now, if we think of what these boundary boundary conditions or boundary theories for our four-dimensional theories, AG and BG check, well, what they should be should be something like, well, first of all, they should be something like three-dimensional field theories with boundaries for some four-dimensional field theory. And because these theories physically are gauge theories, it's kind of a general principle if you think of what the boundaries in a gauge theory. Gauge theory is a theory that's just built out of a symmetry of this group. So roughly what a boundary for a gauge theory should be just a theory of one dimension lower with G or G dual symmetry. So in the two cases. So we're looking for three-dimensional field theories with a certain kind of G symmetry or three-dimensional field theories with a certain kind of G dual symmetry. So we're looking at actions of G or G dual on 3D field theories. But now there are a lot of ways of trying to make sense what kind of actions of a group on a 3D field theory there are. And there are going to be two very different kinds. There's going to be kind of an A-type action and a B-type action. That's the kind of spirit. So, so as an idea, you might try to build this, if you're thinking physically, you might try to build this just like we built representation from quantum mechanics from a G set. You might try to build from, let me call it P sub X, if I have a group G acting on the variety X, so here G is my complex reductive group, suppose I have an action of a G variety X, I might hope that gives me a boundary condition for the A theory. I might hope that gives me a boundary condition for the A theory, and likewise, if I have an action of the dual group on some variety, I might hope to get an action of a boundary condition for the dual theory. That's kind of at least just the spirit. So we're trying to construct, so you might hope to construct boundary conditions just from symmetry, spaces with G or G dual symmetry. Now, on the B side, everything in this story is much easier on the B side. Everything in geometric Langlands, the B side is somehow the answer. And the A side is somehow the question. Now, on the B side, everything can be, you can make sense of this. The B side makes sense as a fully extended field theory. You could talk about what the boundary theories are. And so the boundaries, and I'm not going to try to say this precisely, and I'll explain why, but the boundaries are going to be now, just like before we had in our toy model, we had representations of G. So now we're going to look at two categorical representations of this group. So we're going to look for, and maybe let's call these algebraic, two categorical representations of this group. So I'm going to have actions of this dual group on two categories. And again, what should you have in mind? I'm not going to define this precisely, but again, I have in mind, I have a variety with this action. How do you get a two category? Well, at least if from X, I can look at, for example, quasi-coherent sheaves on X, this X check, that has a tensor product. So my kind of easiest version of a two category is I can look at modules for this. So things with an action of tensoring by sheaves on X check. So here the B, when I say B is the same as in B in mirror symmetry. B means everything's algebraic geometry. It's coherent sheaves and that kind of story. Those are ingredients. So I can look at something that has an action of tensoring by quasi-coherent sheaves on X check. So you might ask, so if G acts on X check, it'll act on this two category. And you can try to axiomize what kind of properties that two category has. What kind of action? How do you formulate an action that looks like this? So that's a kind of prototypical example. And I'm going to completely ignore, for the kind of experts in the audience, I'm going to completely ignore the subtleties about incoherent versus quasi-coherent. These are kind of completion issues that are that's sort of where the technical work in this stuff happens, but I'll completely suppress the difference between in those. So, okay. So, but in any case, in the B side, you can make sense of what kind of thing. So the idea is that in geometric Langlands on the B side, we're doing representation theory, just like in 2D, except that instead of having a 2D field theory, we upped by 2 our game. So we need representations not on a vector space, but on a 2 category. That's great, except that this has absolutely no parallel that we know of on the A side. This kind of structure, to my knowledge, we don't know anything that we can say of that structure. What kind of a thing are you looking for an A-type G action in this on the 2 category, and how you'd fit those as boundary conditions in geometric Langlands. So this is something I have no idea what to do with. So I'm not going to talk about this aspect at all. I'm going to try to get some kind of, so I'm not going to look, so in other words, this is the kind of thing that I would attach to a point. my theory BG check of a point would be something like the collection of all such two categorical representations. But on the A side, I'm not going to have access to a point. As I said, I only have Riemann surfaces and punctured disks. So I'm not going to try to access anything like B of a point. I'm going to access things that are kind of higher up the food chain. Okay, so
there was an intermediate step where we could have looked at G-check acting on quasi-coherent sheaves, so we would have a representation on a category. Yeah. And is there a kind of nice place where that fits into the story, or a toy model where that fits in?
Yeah, absolutely. So so if you're studying, so I kind of skip from 2D field theory to 4D field theory, because that's where geometric Langlands lives. You could have, and many people do, and it's very interesting to study 3D field theory. So if you're studying three-dimensional gauge theory, for example, all this work on Coulomb branches and symplectic duality, 3D mirror symmetry, there's a whole subject which studies, if you like, 3D gauge theories. And a 3D gauge, there are many kinds of 3D gauge theory, but kind of a very bird's eye view, a 3D gauge theory is something that to a point will attach categorical representations of the group. So group actions on categories. And there are different variants of those, and that kind of leads to many kinds of 3D theories. One reason we jumped to 4, I could say it's because we want geometric Langlands, but why do we want geometric Langlands? Is because of duality. Because the way duality works in physics, electromagnetic duality works in 4 dimensions, electricity and magnetism are dual, they're both kind of two-form field strength. In 4 dimensions, gauge theory is dual to gauge theory. So the two sides are both gauge theories. In 3 dimensions, you can still do kind of electromagnetic duality. The kind of duality on the other side is a scalar field. The dual of a gauge field is a scalar field. You don't have duality in gauge theory. You don't have, so you can study representations of G on categories, but they won't kind of have a Fourier dual, which is representations of G dual or something like that on categories. There would be some other kind of thing. In 4D, the beautiful thing that happens, both sides are about representations. And that's why that's where the Langlands correspondence happens. So that's why I jumped to 4D. So that's kind of physically why because we want, in 4D, gauge theory is dual to gauge theory. Representation theory is dual to representation theory.
Can I use the remaining 2 minutes to ask a somewhat unrelated question?
Great.
So when people talk, sometimes people talk about module categories for monodal categories as being boundary conditions.
Mm-hmm. Yeah. In 3D.
So that's a 3D phenomenon.
Yeah, so I have a monoidal category, if you'd like, that has a 2-category of module categories, which I think of as what I attach to a point in a 3D field theory.
Okay.
And then the boundary conditions are the module categories.
Mm-hmm.
Yeah, and that's, if you like, similar to your question. Well, I mean, like, if I take quasi-coherent sheaves, for example, I could think of, well, in fact, this is going to appear, like, if I think of quasi-coherent sheaves on a variety as a monoidal category, and I could look at module categories for that, that defines, I think of that as being part of a 3D field theory. And that's going to be this, so here I'm thinking about the collection of all of those. So the collection, I fix a variety, I look at the collection of 2-category of all module categories for QC. That's a 2-category, that's part of a 3D field theory. That's exactly the field theories I'm going to talk about as boundary. Those 3D field theories I'm thinking of as boundary conditions for the 4D geometric congruent story, if the variety has a group action. Mm-hmm. As opposed to, you were asking about boundary conditions in the 3D theory. So if you like, there's somehow like corners of 4D theory in some sense, boundaries in the boundary. Mm-hmm. So yeah, so the idea is that what I'm going to try to access, I'm going to try to access some version of the, so rather than try to access this entire kind of beast, this 3-category of these 2-categorical representations, which is a little unwieldy, I'm going to try to get some geometric content out of it, some kind of moduli space, like I promised, and those will lead us to much more familiar and less kind of less high categorical structures. So kind of, I think of this kind of the sweet spot here as being, I'm going to look at the 2-sphere. I'm looking at these field theories and think of what they do on the 2-sphere. And so now let's just think first about a 3-dimensional field theory. So here the 3-dimensional field theories that are arising are going to be the ones that are, think of the ones that come from varieties, and secretly these varieties are coming with an action of the group, but the 3D field theory, the boundary, will have to do just with this variety. So if you have a 3D field theory, then the value on the 2-sphere has a nice structure. It's a structure of an E3 algebra. So this is exactly the same picture that we had before. We now just draw it 1 dimension higher. You have a 3-dimensional field theory. If you excise a couple of points, so this is the 3D version of a pair of pants. This picture is a bordism from 2 2-spheres to another 2-sphere. So it defines an operation on Z of S2. So in the 3D field theory, Z of S2 will be a vector space, or maybe I'm thinking about them as being a chain complex. So I'm doing everything kind of derivedly. So it's a chain complex with operations labeled by, so I have these operations, again, labeled by configurations, by chains on configurations of K points on R3. That's kind of what this picture is, or on a disk. Well, that seems complicated, but let's just look on the level of homology. In the homology, and let's just look at binary operations. We look at binary operations, so that's just configurations of 2 points in R3, which looks like a 2-sphere. And so the homology has 2 elements. There's the H0, which is called product, and there's something in H2, which is homology, so think of it as degree -2. So I have 2 operations on this vector space on the level of homology, which is a commutative product and a Poisson bracket. So this actually defines a Poisson algebra. It's graded. It's not super anymore. The signs are normal. But it's graded. This guy has, if I keep track of the degree. But I'm going to often forget about the degree and just think about this as a Poisson algebra. So if I start from a 3-dimensional field theory, I immediately get something very nice out of it. I get a Poisson algebra out of it. And so this is the algebra of local operators in 3 dimensions. So in other words, if I start with a 3D field theory, I can attach to it this moduli space. I can attach this spectrum of Z of S2, which is something like a graded, if I might again ignore the grading, it's a Poisson variety. Now, maybe again, let me put some caveats that really I maybe don't want to pass to homology. I want to look at the chain level. So really, this is something slightly non-commutative. Really, it's something that maybe you call an E3 variety. Functions on it are not quite Poisson. They're something on the level of associated graded looks Poisson. So this is what the shifted symplectic people would think of as the E3 quantization of this shifted symplectic or shifted Poisson variety. So I think of this as being kind of slightly non-commutative, slightly quantized, but I'll kind of suppress that distinction. Okay, so that's what this so the moduli space, given a 3D field theory, I can produce out of it a Poisson algebra, and think of that as a Poisson variety. So what is, in our case, we started with X check of variety. The checks, just I want to remind me that I'm thinking about the B side. And I have, so I'm going to produce out of it some algebra. So let me call this theory, let me call it the ELF, this theory. This is my 3D field theory. So here I have a 3D field theory. Let me tell you that what I'm going to attach to it is I want look something like maps. I'm looking at something like maps from a two-sphere into my variety. And I want to linearize that. That's going to be my space of fields. Linearize it, I'm not going to take functions, I'm going to take distributions or volume forms. So this is some variant because now everything has geometry. I have to be careful, what do I mean by function? So here I mean something more like measures, but this is going to have some kind of convolution structure, going to have some kind of multiplication structure. And that's going to be my Poisson algebra. Now, what do I mean by maps from the two-sphere? So here this means maps in the sense of derived algebraic geometry. So here, two-sphere is taken really as kind of as a homotopy type. So if you like, it's going to be, I can write this as some kind of iterated derived fiber product. So it's not something very, it's not really like, you shouldn't be thinking of like smooth maps into a target, but something very derived. Really, this is going to be modules. This is really going to be some kind of a spec of some symmetric algebra. Let me just tell you what the answer is. If you use Koszul duality, you can write what this vector space is. This algebra is just functions on the cotangent bundle of X check with its multiplication. So now I've rewritten it, it's kind of done maybe some kind of Fourier transform. Instead of convolution algebra, I have a multiplication algebra. Secretly, this cotangent bundle is, if I keep track of gradings, this cotangent bundle has been shifted twice. So that's where I want to get not an ordinary Poisson algebra, but a two-shifted Poisson algebra, this E3 algebra. But so you get functions on this, but again, I'm going to try to suppress this grading as much as I can. So basically you get functions on the cotangent bundle of X check with its standard Poisson structure. So it has multiplication and it has a standard Poisson bracket. So in other words, what I'm saying is that this moduli space for this theory, the moduli space that my prescription tells me to do is, I'm just supposed to take this algebra. I've written it as algebra with multiplication. So now I know what its spectrum is. Its spectrum is just the cotangent bundle of X check. Okay, maybe let me put in that shift by 2 move. So the moduli space that I produce out of this variety is just the shifted cotangent bundle of X check. So functions on it are symmetric algebra of vector fields shifted twice. Okay. Now you might object that maybe my variety was not affine. And so maybe this taking spec of functions is not such a smart thing to do. Let me maybe just tell you that you don't need to deal only with affine things. If you take the same field theory and you evaluate it not on the two-sphere, but on the circle, you now get a category. And again, that category has a multiplication. Now it's an E2 multiplication. The category ends up being something which is just sheaves on this cotangent bundle. And again, you have to be careful about what to do with the gradings. So let me use that, the quotation marks, to say I'm going to deal with the gradings correctly. But it's this basically with its tensor product. So in other words, this guy is much smarter than just functions on the cotangent bundle. This guy knows the cotangent bundle itself, even if your variety is not affine. So this is just to reassure you that starting from this theory, I really see the cotangent bundle of X check by doing this moduli space construction. Okay. So in physics, you really take the point of view that rather than starting with X, I started with this variety X check, but I produced out of it something else, let me call it M check, which is this shifted cotangent bundle. And so now I have a holomorphic symplectic or algebraic symplectic variety. And this is my moduli space, but this is really the star of the show. We think of this theory as being not about X check, but about M check. So we change our focus. And this is what's called the Rosansky-Witten theory. This is Rosansky-Witten theory, 3D topological field theory, attached to a holomorphic symplectic variety M check. That's the theory we were discussing. So it's something like geometric quantization. In usual geometric quantization, I take a symplectic manifold and produce a vector space. Now I've done kind of a two-shifted geometric quantization. I take a symplectic variety and produce a 3D field theory. Instead of a quantum mechanics, I'm producing a 3D field theory. So it's kind of twice categorified version of geometric quantization. Okay, so that's kind of the prescription of how to get some algebraic geometry out of this field theory. Now, but really what I was interested in was this 4D theory. So here remember that this X check was playing the role of a boundary as something on which G check acted. So let's forget about this and let's focus now on the group itself. What can I get out of the group itself? So I'm going to look at my theory, my B theory, and I'm going to look at its value on the two-sphere also. So this is what in physics you might call the category. So first of all, it's a category because we're doing a 4D field theory valid on a two manifold, and its category, it's known as line defects, or in this case, lines are codimension 3. A line is codimension 3 in four dimensions. So these are codimension 3 defects. So what is this thing? So let me just draw some picture of, so here I'm thinking of having, here I have a Riemann surface, or algebraic curve, so maybe, or two manifold, maybe cross an interval. So this direction is my interval, and this is my curve. And what is this codimension 3 defect? So this is, I take a point in this 3 manifolds, Riemann surface cross an interval. And if you'd like, if I'm thinking in 4 dimensions, physicists will always think in 4 dimensions, and secretly there's maybe a line moving in the 4th dimension. So think of this is a line defect in 4 dimensions, but I'm not going to draw this 4th dimension. So I have a point here, and I'm going to think about this B theory on, so again, the way I understand defects is I cut out a little ball around this defect. Its boundary is a two-sphere. And now I have a kind of cobordism from C union a two-sphere to C. So it gives some operators on whatever I attach. So it tells me that whatever my field theory attaches to C gets operators on it from what the theory attaches to the two-sphere. And also another variant of the kind of pair of pants picture, again, tells me that whatever I attach to this two-sphere, I can think of these clumping them together. And this guy is going to have some structure of one of these, an E3 category. It's going to be a category with operations labeled by these pictures. Okay, so now I want to try to convince you that this is something that's very familiar in geometric Langlands, this picture. So how do I get from this to something familiar? I'm going to squash this direction. So now what is my field theory? Again, what I'm supposed to do is I'm going to take these spaces of local systems. That's what my B theory does. Take the spaces of local systems, and I'm supposed to linearize them. The way I linearize them is look at some category of sheaves. So really, this is going to be category of sheaves on local systems on the two-sphere. Okay, so that's what these categories are. And now local systems are kind of topological. They're homotopy invariant. They're about pi1. So I don't need to keep all this space around these manifold pictures. I can collapse this. So let me draw the collapsed version of that picture. So here's my surface C. So again, I'm taking this exact same picture and I'm just shrinking the time dimension, shrinking the interval. And what do I get? I get a version of C. This is, I don't know, people call this the ravioli or the UFO or I don't know, the blob. So I'm going to take a picture of C, And this is trying to be my picture for C glued to C and the complement of a point, this non-Hausdorff guy, where I take 2 copies of C and I glue them away from this one point. So I have a little kind of blob here. So that's what's been left of my 2-sphere. So what you get out of this, so this, if I look at local systems on this weird picture, they map to local systems on C in 2 ways. There are 2 sheets I can project to. And so if I have a sheaf up on this space, it defines an operator. By push-pull, it defines an operator on sheaves here. So this is exactly the picture of Hecke modifications. I'm looking at, except that it's the side that we don't usually talk about Hecke modifications. We have a local system on a surface, and we think about what are all the Hecke modifications, all the ways of modifying at a single point. So pairs of local systems that are identified away from this point. Okay, and I'll spell out what this category is exactly that's acting. But what is the, but in any case, so before I had this, here I had this picture, this E3 picture. I had this picture labeled by these little disks inside of a big disk. Once I've squashed the direction, I don't see the same, I don't see it quite in the same way. I don't see disks inside of a big disk. Once I squash it, I see, I don't know, I have this kind of very crustacean-y picture of this. I have these little little critters moving around on C, and they kind of roam around on C. So this guy is maybe at a point X, and this guy is at point Y, and they can kind of move around on C, and then they can kind of climb on top of each other. So there's in 2 directions here that these points can collide. So I have something at X and something at Y can collide. I get 2 directions where I have a picture of factorization. So I'm not sure I'll have time to really explain factorization algebras. I know Emily gave a series of talks about them in your seminar. So so there's 2 directions where where these guys multiply just by colliding, but there's another direction where I can stack them on top of each other. So I can think of do a modification like this and then compose it with another modification on top of it. So there's kind of 2 directions of factorization and 1 direction of kind of ordinary convolution. So what this is supposed to tell you is that this category that I'm looking at, this category attached to the 2-sphere, is what you could call a factorization monoidal category. So it has 2 operations. One is factorization, and one is things colliding on the surface, and another is monoidal. Maybe just to say, this should remind you of the picture when you learn 2 categories. You know that there's kind of ways of composing arrows in a 2 category. You can kind of compose them one way like this, or you can compose them this way. They're kind of 2 directions of composition in a 2 category. And that's exactly what we're seeing here. Here we have a picture that has 3 directions of composition. That's the E3. It's kind of an algebra which has somehow 3 directions of composition. It looks something like it's a kind of 3 category. Okay, so since time is short, maybe I'll skip saying exactly what a factorization algebra is till questions. Let me just say what is this guy? So I promised. So what is this space, first of all? Local systems on the 2-sphere. Well, what is a local system on the 2-sphere? Well, let me just draw a 2-sphere, kind of slightly squash 2-sphere. So I have a disk and I have another disk, and they're glued along a circle. A local system on the disk, there's really nothing much to a local system on disk. It's contractible. I have just a single one of them, but it has automorphism group, which is the dual group. Here I have another one. Another local systems here is another copy of point mod G-check, but they're glued together over local systems in the circle, which is conjugacy classes. So it's an intersection of point cross point in conjugacy classes. Or if you write it a little more explicitly, it's self-intersection of 0 in the Lie algebra. So this is a derived self-intersection. Maybe just put an L to say it's a derived intersection of a point in the Lie algebra up to this. So that derived intersection of a vector space is really just in the derived world, it's modules for some exterior algebra. So this is an exterior algebra. So if you'd like, it's the vector space G-check shifted by 1 and worked on conjugations. So this is what this space looks like. So it's not very big. There are not a lot of local systems on the 2-sphere, but there's a little bit of interesting derived structure. And you can calculate what sheaves on this thing are. So here, So I want to calculate what sheaves on this. So here I have, this is modules for some exterior algebra. Modules for an exterior algebra can be exchanged with modules for a symmetric algebra in the derived world. So let me just write this down. So this category I have, this B, G check of the two-sphere, it's quasi-coherent sheaves. Maybe let's put a shriek here. It's really intercoherent sheaves. Again, I said I'd ignore completion issues, but so roughly quasi-coherent sheaves on this space. It had a structure which is a version of convolution. I can rewrite that as just modules for, instead of, this is modules for some exterior algebra, I can write it as modules for symmetric algebra. So I write it as modules for some symmetric algebra, mod the group, and now this convolution structure becomes tensor product. Or this is something, finally get to something that looks more concrete. I take the coadjoint representation, so the dual of the Lie algebra, and I look at equivariant sheaves on it, where I put quotation marks to say I've ignored the grading. So I have to put things in some degree too. But here it's now with tensor product. This category. So in other words, this category that we're looking at, this category of Hecke operators in the B theory, is sheaves on this coadjoint representation with their tensor product. Okay, so let me just get, so the point is of all of this, that if I try to understand what my moduli space for my B theory should be, this kind of tells me what the answer is. I've written operators in this theory as sheaves on a space with tensor product. So I'm just going to take that space, in other words, just the coadjoint representation. Again, maybe let me just point out that it's shifted by 2. That's my moduli space for the B theory. So that's Masoud's question from a while ago. What is the moduli space? In this B theory, it's just a coadjoint representation. Now, again, secretly, I'm ignoring the difference between symmetric monoidal and E3. Really, it's really some kind of quantization of this thing, some kind of geometric, some kind of quantization. This space is really the cotangent bundle of point mod the dual group with some shift. It's a 3-shifted die, and the category I want is really some deformation quantization of that. But on the level of just monoidal categories, this is the correct monoidal category. It has some extra bells and whistles on it. Okay, so maybe I should pause for a second. Did that make any sense? So I extracted from the B theory a geometric object, which is this coadjoint representation, and which in a similar way I extracted from a variety, Poisson space, which is its cotangent bundle. Is that questions on that before I move on? Okay, so let me now just, so now I just want to put this together, put it all together on the B side. So I start, and now I have a pair of a variety and a variety with a group action. So out of this variety, I constructed the cotangent bundle. But if a group acts on a variety, then the cotangent bundle carries a Hamiltonian action of the group. So there's a moment map, which is equivariant for the group. So instead of just thinking of G check acting on X check, I want to think about Hamiltonianly, or if you'd like, I could just take this, and again, I like to call this guy M check. Or another way to write this is if I take the quotient M check mod G check has a map to my coadjoint orbit stack, where I'm ignoring shifted by 2. So the idea is that, so this is where I see the structure Hamiltonian G-check space. I can encode the Hamiltonian G-check space in terms of just a map to the coadjoint quotient, which is compatible with the Poisson structure. Okay, so this is the way Hamiltonian actions are going to come up. So if you'd like, I could capture this algebraically. This is kind of, if you like, geometrically. If you wanted to say this algebraically, before we had functions on this Poisson variety, which was a Poisson algebra, but now it's enhanced from a Poisson algebra from Poisson or E3 algebra to an object, let me call it the push forward of the structure sheaf under the moment map. Now it's an object of this category of sheaves on the coadjoint orbit, which is now an E3 algebra object. So it's a Poisson. So this is a fancy way of encoding all the structure I've said before. So or if you don't like the words E3, this is another way in algebraic geometry. We could say this is something that has factorization, something that can collide on a surface, and it's also an associative algebra. So I have a factorization associative algebra in this category. That category was a factorization monoidal category, and it makes sense to talk about factorization associative algebra. Or if you prefer, you could just look at the whole category of sheaves on M check and on G check. It's now a module category for QC of G check dual mod G check. This is just tensoring over the moment map. I take a sheaf and I pull it back and tensor with it. And this makes it into a factorization module category. So there you can, this is the algebraic structure that we see here out of the boundary condition. Okay. All right, so this is a very maybe long-winded way of, I started with a variety, and everything I'm written here is things you could just say starting with a variety X check. So what's the point of doing all these abstract games and saying it in this complicated way? And so I don't really know how much time I have. Actually, maybe I should ask, how much time do I have? Or am I over time already?
You're mute, Jody. About 10 minutes.
Okay. All right. So let me try to explain what this game was for. The reason to do these games is that these structures that I've written down here, all the structures that I've explained on the B side are structures we can make sense of on the A side. So I won't have time to explain. You can give a mathematical definition of a 1-2-dimensional part of a field theory. So I can try to say what a field theory is if I only have access to these curves with marked points on them, which is the structure I see on the A side. But you can formulate a lot of structure, field theoretic structures over there. And everything I said is things that are accessible just with that part of the theory. And these are things we can see on the A side. So this is what I'd like to explain in the remaining time, is how we see the same kind of structures on the A side. So first, let's say, so here again, let me say what the A side is. Given a Riemann surface or algebraic curve, we're going to look at some category of sheaves on bun G of C. Now here, sheaf can depend on the context. You could talk about D modules, or you could talk about some version of constructible sheaves. For example, ellatic constructible sheaves, if you're doing in positive characteristic. And that's kind of more of what I have in mind. But let me be a little agnostic here. What kind of sheaves we're looking at? But something more like D modules or constructible sheaves. Now, this is the category we attach into the field theory attaches to a surface, and this has the familiar Hecke symmetries. So here, this is the picture that one usually draws. You have a Riemann surface C, and we think about modifications of G bundles at a point. So we look at G bundles on the same kind of ravioli picture. I have two copies of the curve glued away from a point. And this looks like bun G, so it looks like a Riemann surface, but also with, maybe I glue over some bun G on some disk, the affine Grassmannian. So the affine Grassmannian, this is playing the role of bun G, not quite of a two-sphere, but of this kind of squashed two-sphere. So let me call this the affine Grassmannian. Really, this is the affine Grassmannian. This is maybe called the equivariant version of the affine Grassmannian. So it loops into G, double cosets loops into the positive half. So this is the equivariant Grassmannian. So Hecke, the theory of Hecke operation tells me that if I look at sheaves on this equivariant Grassmannian, so let's call this the spherical category for G. This acts these are my defect operators. This acts on AG of C, on my category attached to any algebraic curve. And it has exactly the same structure that we saw in the B side. It has a factorization structure, and it has a monoidal structure. So you have kind of three directions of compositions. So this is a factorization monoidal category, or some version of E3 category. So the
David, can I just ask quickly? So this is more like a kind of equivariant version of the Bredinson-Drinfeld affine Grassmannian.
So this right now I've just drawn the 1-point version, 1-point equivariant version of the Grassmannian, but the factorization structure is the equivariant version of the Beilinson-Drinfeld Grassmannian. Yeah. So the point is that there's the Beilinson-Drinfeld Grassmannian has factorization, but if you look at the equivariant version, it also has convolution. If you look at double cosets, then you also have this convolution structure. So the whole Beilinson-Drinfeld Grassmannian is just kind of E2. There are only two directions of composition. But if you look at equivariant sheaves, you get three. And so the geometric Satake theorem of Kari and Ivan Mirkovic tells us, that the category we get this way on the abelian level. So if you look at perverse sheaves on the abelian category level, perverse sheaves on this equivariant Grassmannian has all these three different ways of composing. It becomes very commutative. It just becomes a symmetric monoidal category, and it's equivalent to representations of the dual group, or if you want to say it fancily, sheaves on point mod the dual group. Okay, so that's the abelian story. The part that that we're going to need that to line up with what I said before, you need the derived geometric Satake. I don't like when people don't write people's names in full, but I wrote them in the first page. So this Finkelberg's derived geometric Satake theorem tells me that this thing that I call AG of the ravioli or whatever, this object of two local operators matches what we had on the B side. These local operators, these line operators on the B side. Maybe I'll kind of abuse notation and just call this the two-sphere. In other words, the sheaves on this equivariant Grassmannian, the thing that acts on the A side is identified with the thing that acts on the B side. Okay. So the thing that we had there, and now this is a theorem. This is Finkelberg proved this as monoidal categories, and there's some work of Gates, Lurie, and Raskin and Campbell to actually, you really want this as an equivalence of factorization monoidal categories or E3 categories. That's not very well documented, but this is a composition. This is compatible with all the structures that we have, and we need this in order. This is exactly why we need this in order to formulate the geometric Langlands correspondence. Geometric Langlands correspondence. And it's this equivalence of field theories. In particular, equivalence of field theories should tell you that you have this action, that you have an equivalence between the category of Soto Riemann surface on the two sides, and it's compatible with the action of this, let's call it the spherical category, at every point x in C. This category attached to it. This is the category attached to the two-sphere. So it's A of the two-sphere or B of the two-sphere, and it acts for every point on the curve. So this is the geometric Langlands conjecture. Okay, so that's how we see. The spaces that we saw on the B side also appear on the A side. Now, so what I want to finish with what about boundary conditions? Boundary conditions. So I'm going to start. Again, our guess was we start with a G variety X. Now let's put lots of adjectives on it. First, I want to have it to be, let's take X to be smooth and affine, which makes sheaf theory be easier to make sense of. And I'm going to, and most critically, it's going to be a spherical G variety. So this is a very strong finiteness condition. Let me say in a second what that finiteness condition means. So the expectation is that given such a thing, we construct a boundary condition, P sub X, it's a boundary theory for this A theory. And again, the A theory only makes sense on 1 and 2 manifolds easily, and so we'll only try to make sense of this on 1 and 2 manifolds. And so what I'd like to say, what kind of object is this and how we're going to try to match it. So so again, I'm not allowed to access something on the level of a point. I'm only allowed to access on the level of a circle or a Riemann surface. So what kind of objects is this? I'm going to look at loops into X, if you like, X over Laurent series. And inside of it, I have positive loops, X over the kind of arcs. So I have loops and arcs, X over Taylor series. And we're out of these. So this guy is acted on by the loop group. This guy is acted on by the positive half of the loop group. And so we can look at the category, for example, category of sheaves on LX. This is something that you can now make sense of, and not only make sense of as an abstract category, it's something which has an action of the loop group. It's a categorical representation of the loop group. So starting from X, I didn't know what to attach you on, what to tell you to do on a point. But once you go to a circle, to loops, I'm going to say, let's look at sheaves on the loop space of X. That's acted on by the loop group of G. And that's an object, and that's part of the data of this boundary condition. This is still a little scary. What I'd like to look at something a little less scary, which is a part of this. Look at not all sheaves, but sheaves that are equivariant for the positive half of the loop group. So what you would call spherical sheaves. And why is this less scary? Is because this set of orbits is discrete whenever my, I don't know if it's if and only, but certainly if for X spherical. So the finiteness condition I impose on X means that the set of orbits I'm looking at is a discrete set. The kind of spaces like sheaves on the Grassmannian. It's a kind of space that you're used to dealing with in representation theory. So this category is something I can make sense of in this spherical case. And this guy is now acted on by sheaves on the equivariant Grassmannian. In other words, my spherical category. Okay, so yeah. So I think I ran out of time at the same place I ran out of time in the SMRI talks, despite having a lot more time. So let me try to say a little bit about the punchline, and then we can I can say however much people want to hear in discussion. So what I want to explain is that given a G variety, so let me just kind of summarize. G variety, given a G variety X, you can extract out of it this category. Let's call it spherical of X, which is sheaves on LG plus orbits on LX. And this guy is acted on by the spherical category. And it's compatible with factorization structures. So this is a factorization module category. There's also a distinguished object in here, which is the constant sheaf on arcs, L plus of X. Let's call this delta X. This is kind of a unit object. And so you can extract out of this endomorphisms. Let me just write some letters and I'll explain them later if people want. You can extract out of this guy an algebra. You can extract out of this, this is going to be an E3 algebra. Or if you keep track of the spherical action, you could get an E3 algebra in the spherical category. So you can construct, you can take the geometry on the A side and you can construct out of it the same kind of structure, same structure as we saw on functions on M-check for M-check a Hamiltonian G-dual space. So in other words, in fact, I can construct the algebra of functions on a Hamiltonian G-dual space. In other words, I can define. So this gives me a procedure. I start from X and I construct out of it a space M-check, which is spec of this algebra that I got above, which is an affine Hamiltonian G-dual space. So this is this construction of moduli space of the boundary field theory. So this is given a G variety X, you can construct a Hamiltonian G-dual space M-check. And so now you can make some very precise conjectures so work of Gates, Green, Nadler, and Sikaliridis Venkatesh let you predict exactly what this variety should be. So you can say combinatorially in terms of your spherical variety, what you expect M check to be. And so now you can make a bunch of duality conjectures. So you can really make this kind of conjecture that's saying that under this equivalence of field theories, the theory determined by space X matches with the theory determined by space X check, or maybe I should say by this M check. And it gives you a bunch of explicit conjectures. For example, this category, spherical sub X that I described, should be identified as quasi-coherent sheaves on this M check mod G check under this duality. And this should be compatible with factorization and a whole lot of other structures, which are in the second half of my talk. Anyway, I should probably stop, and then I'm happy to discuss that ad nauseum at questions.
So I had a question, Anthony here. It's just about the fact that the M check that you produce in this way is not necessarily the cotangent bundle of anything. So it seems like you end up with more things on the B side than you have on the A side. Is that a problem?
That's right. That's right. Yeah. So it's kind of a little bit of a hodgepodge of things that, you know, the case that you understand the most of is when you happen to have a spherical variety X and its dual, which is often spherical, you know, this M check might be a cotangent bundle. Those are the cases you're kind of easiest to describe. Those are the ones where you can really write everything explicit. And you can say examples of when you expect that to happen. So that does happen. But in general, the duality is not really duality between G actions and G dual actions. It's much more like Hamiltonian G actions and Hamiltonian G dual actions if you want it to be symmetric. So here I started with an X. Really, I should have started with an M, with a cotangent bundle of X. So it's harder to write down what category I want to attach, but because you need to do some. So, but you might be interested. So, but the kind of general kind of classes of boundary conditions in the A theory include not just G varieties X, but really Hamiltonian G spaces, which could be a cotangent bundle of a G variety, but in general needn't be. Mm-hmm. So that you get a much more symmetric picture if you put Hamiltonian actions on the two sides. Now there it's a little more complicated because then I need to tell you what the category of sheaves I attach to M. And really you should think of, you know, this is kind of some micro-local category. Mm-hmm. So I need to decide what procedure I'm going to take M and do some kind of quantization to it and attach to it some category. That's easiest to say if I have a cotangent bundle. I just say D modules. But really really the same subtleties appear on the dual side, and I kind of suppress them in the distinction between having a symplectic space and its quantization. You know, this difference between a Poisson algebra and an E3 algebra. And the kind of things we get on this dual side are a little more than a Poisson algebra. It's a Poisson algebra together with this kind of this deformation quantization. And you really would have needed to put that in on the A side also. So anyway, this is just to say that there's a place where you really expect a full symmetry. The two sides to be symmetric. You somehow expect that on one side you have sort of boundary conditions for the A theory and boundary conditions for the B theory, and this should really match. If you have an equivalence of field theories, you expect the boundaries to match. Inside of here, there's a class which are given by Hamiltonian G actions. Sorry, my Venn diagram doesn't look very good. So here you have all boundaries. Inside of boundaries, I might have Hamiltonian G spaces, and inside of Hamiltonian G spaces, I have cotangents. And you have the same kind of hierarchy on both sides. And there's no reason for any of these, you know, these inner things to match perfectly. So sometimes cotangents go to cotangents. More generally, cotangents go to Hamiltonian spaces. Now you might, maybe this is very confusing because I've been talking all the time about Hamiltonian spaces. Where did those come from? I extracted on the B side, I extracted a Hamiltonian space from my boundary condition. I can build one, an affine Hamiltonian space out of the boundary condition. But that might not, for example, that's affine. I might have forgotten some information. So a boundary condition is something slightly more complicated, which there's a functor from them to Hamiltonian actions. But a boundary condition in general has more to it than a Hamiltonian action. So that's what's confusing here, that you can always attach Hamiltonian actions to boundary conditions, but a boundary condition has slightly more. And you only really expect this duality to hold on the level of boundary conditions. So yeah, I don't know if that addresses your question. The way we are accessing this is we start with a G space X, an honest G space, rather than its cotangent level. It's a Hamiltonian space. Out of that, we construct an M check. And in a lot of cases, you can describe this very explicitly. For example, using this kind of theory of the regular group scheme of regular centralizers, you can exactly describe the kind of regular part. If you look at under the moment map, the inverse image of the regular locus.
Yeah.
That locus you can describe explicitly and you can prove exactly everything you want on the regular locus. So somehow these Hamiltonian spaces, there's a regular part, which is something you completely understand, and then there's the non-regular part, which gets more and more complicated. And in general, even all of that might just be like an affinization of something more complicated, which is not a space. So there are kind of various shadows you can build, and that's sort of what we're trying to build. So I think you can make some precise conjectures, but the general, to really make a picture that really lines up, you need to kind of grapple with what these boundary conditions really are.
Further questions?
Oded here. I just have actually a question about the first page of the talk.
Great.
You mentioned the Coulomb branches in the beginning. You don't have to actually go to that. How do they fit into this picture?
Great. Yeah, so, right, so, yeah, so here's, yeah, so the question is, for example, what is the relation between, say, symplectic duality or 3D mirror symmetry and this Langlands duality for boundary conditions? So in symplectic duality, we have, there's some duality operation on not G spaces, but just on symplectic variety or symplectic cones. So some variety. So the picture of symplectic duality is something about 3D field theories. The field theories are usually given as gauge theories. So that's where with the terminology Coulomb branch, and so on, it means that there's a group around. So you've built your space, like like a Nakajima quiver variety. You've built it by Hamiltonian reduction from some Hamiltonian G space. But the space itself, you're just using its symplectic variety structure, not a G action. So you have this theory of symplectic duality, that given a symplectic variety, you build this dual one, this Coulomb branch, and you expect some relation between 3D field theories on these two. Now, what we're talking about here, the 4D story, so that symplectic duality story fits in as into a duality about the 4D theory. So maybe let me just write something. So we have so we have this. So we have a boundary for this A theory, and we have a boundary for this B theory. These are now Hamiltonian, something like Hamiltonian G spaces, Hamiltonian G dual spaces. You can try to decouple it. You can try to get, yeah, sorry. So what I want to say is that there's a duality on 3D theories, and there's a duality on boundary conditions in 4D. And those are compatible in the following way. It's not that the underlying 3D theories are equivalent. It's not, given a Hamiltonian G space and the Hamiltonian G dual space, those are not the Coulomb and Higgs branch of each other, so to speak. It's not that you just forget the G action and you're supposed to dual them. Forgetting, so rather there's an operation from a boundary of 3D, there's an operation to a 3D theory. You can make an operation to get a 3D theory. Here sorry, let me try to draw a schematic picture. So here's my, I'm thinking of the 4D theory, and then I have a boundary condition. Let me call this P sub x as a boundary condition. So this is some picture that only makes sense on the boundary of some kind of bulk here. In order to get a purely 3D theory, I should put something on the other side. I look at the AG theory on an interval where on one end I put this and the other end I have to put something else. So just like if I have a representation of a group G, if I have a representation of a group G, what vector space do I attach to it? There's many vector spaces I can attach to it. I can attach a vector space. I can attach, if you'd like, the underlying vector space. That's Hom from the regular representation to V, or if you'd like, functions on the set V. But I could also take the invariance. It's another perfectly good vector space I can attach to a representation, which is Hom from the trivial representation, or functions on a point to V. So that's what this picture is supposed to say. On the other side, I could put something like some version of the regular representation, that's called the Dirichlet boundary, or I could take some version of the trivial representation, that's the Neumann boundary. Okay, and this picture will have to match with what you have on the dual side. You have to, so the claim is that on one side, if you just take the 3D gauge theory, okay, the 3D gauge theory you get to the boundary condition, on the dual side does not correspond to just forgetting the Hamiltonian space, but to doing a Whittaker reduction, to restricting it to the Costin slice. So let me just write this. Where's it? I need a page. So there's an operation which is not the most naive operation you might have thought of for a Hamiltonian space. If I have a Hamiltonian space, there's an operation I could do, which is I can restrict to the Costin slice. Costin slice, which looks like Cartan W. I could restrict this. So let's call this M check constant. And this guy is now just a pure, this is now a symplectic variety. And this is the one that's going to be symplectic dual to your T star X. So if I start with T star X on one side, the symplectic duality, so sorry, I should take the quotient. So I take the Hamiltonian reduction by G will correspond to this M check constant. This will be the Coulomb branch story. So this is just to say there is a precise compatibility between the Coulomb branch story, except that in the Coulomb branch story, you've done some Hamiltonian reduction. You've taken a quotient, a hyperkähler or symplectic reduction by group. That operation on the dual side, it translates it into an operation on the dual side. It has to. Any operation on this side has to translate an operation on the dual side. It's not taking naive Hamiltonian reduction or forgetting the action or something like that. It's taking this constant restriction. And this is exactly what's in the BFN story.
So you can actually recover the BFN construction in this one?
Yeah, I mean, yes. I mean, for the spaces that are appearing here, this is the same. It's the same construction. I mean, the philosophy that I was explaining is the same. They're both the philosophy, just a moduli space. What does BFN do? They're trying to explain mathematically the notion of moduli space of vacua in a gauge theory, which is what I was doing, right? I was saying you have a 3D theory, you have this notion of moduli space of vacua called Coulomb branch. I didn't use those terminology. That moduli space, it just means you take the algebra of local operators and you take its spectrum. So what BFN do is they tell us what does those words mean? The algebra of local operators, this is the homology of some decorated version of the FN Grassmannian. And you take its spec. And that's the same kind of construction I was doing here. Here I was just saying, what I was doing actually here, if you know their paper on ring objects in the Sataka category, is very, very close to that. I was saying, let's take the corresponding ring object in the Sataka category. That's its functions on my M check. So it's really kind of the same kind of construction, just done in a slightly different. It's done in 4D rather than in 3D. So we're keeping track of more structure than they are.
Great, thank you.
Is there a simple example of a funny equivalence that we didn't know already that's predicted by this?
Yes. Right. Yes, there are. Do I remember one that? So I think if in my slides for my Berkeley talks, I wrote a bunch of examples. There are some very interesting pairs that are matched this way that are not. So the main difference with the symplectic duality story is that in the source of examples, the symplectic duality story is primarily about linear Hamiltonian actions, right? So you had a representation, you have a symplectic representation of a group. Mm-hmm. And again, you really understand it best when it's a cotangent bundle of just a representation of a group. So it's a linear version. So here we can give a bunch of examples. Again, this is all conjectural, right? So making predictions rather than theorems, but you give a bunch of examples of nonlinear versions. So rather than symplectic representation, we're looking at cotangents of spherical varieties. And you can say for various cotangent spherical varieties or more general kind of Hamiltonian G spaces, which should correspond to. So the most interesting one, I think, the one that I think got the number theorists most interested, that I think that certainly for Akshay and Yanis, the one that seemed most suggestive is when you take on the A side, you take the space of the theta correspondence. So that's not a cotangent bundle. That's a so let me not try to write down anything very precise because I'll get the groups wrong. But you take the context, you take the kind of the setting of the oscillator representation. So there you do have something linear, the theta correspondence, but on the dual side you get something nonlinear. You get these spaces that appear in the Gahn-Gross-Poiseuille problem. So there's an interesting class of spherical varieties that have to do with restriction problems. So you take, the easiest one is, restriction from GLN plus 1 to GLN. There's a bunch of multiplicity 1 restriction problems for classical groups. So those multiplicity 1 restriction problems can be said in language of there's a spherical variety so just look at, say, an orthogonal group SO2n with an action of SO2n and SO2n minus 1. That's an interesting spherical action. And those are very interesting, very, very important in number theory. That's this part of this Gahn-Gross-Poiseuille conjectures. And under this correspondence, those match up with the theta correspondence, which is also very well studied, but this somehow explains some of their similar features. So, and there's a bunch of other, I guess the most classical, the one I talked about in SMRI, the most classical one is the one that just, for example, Hecke, just the standard representation of SL2, the defining representation of SL2 matches with PSL2 mod the torus. So that, if you like, is in this language explanation of Hecke, why the L function, Hecke's L function of the modular form, which has to do with the torus period of the modular form, and PSL2 matches with kind of standard L function for a two-dimensional Galois representation. So that's another nice example. There's this generalization that one example that there is now a theorem recently did the Tate case. That's the local version of our conjecture is a theorem of theirs very recently, and that's just look at the multiplicative group acting on A1. Right. So, and that's dual to itself. And more generally, you could have various hypertoric cases. This kind of the basic one.
Sorry, so it just dropped, one crucial word dropped out. So you said the Tate, so who did this Tate case? Or
Justin Hilburn and Sam Raskin. They proved the local version, maybe they already by now the global, but they explained the local version of our conjecture. I mean, there are various versions of our conjecture that are theorems of other people's in very special cases. For example, derived geometric Satake itself is also, we think of the group as a spherical variety for the group times itself, then our conjecture boils down to Satake. There's a case where, here's another interesting, this is not exciting at all geometrically, but you can take the G variety to be a point. And then the dual one is the Whittaker space, is the cotangent bundle of the group Whittaker reduced by n. So that's basically what I was trying to say to Odette's question.
Mm-hmm.
So it's called the Neumann condition. The point is the one that corresponds to the Neumann boundary condition. The other one, you have this kind of restriction to the constant slice, which is this Whittaker reduction. So point and Whittaker spaces on both sides, you can do it on either way. Whittaker on the A side or Whittaker on the B side are switched with point. So that's an example of this duality. And again, the local versions of our conjecture in those cases are theorems. I mean, what is Kari and Ed and Dennis, and I mean, so you can interpret various statements about Whittaker sheaves as, proving a case of this.
Mm-hmm. So for the Whittaker version on the other side, you get the non-derived, the abelian, the Sataki where you don't have derived categories.
Exactly. Yeah.
Mm-hmm.
Yeah. So and that's why you get a point, right? So dually you have this. The dual variety is point mod G-check mapping to. You've thrown away all the interesting all the derived stuff. So if you do Whittaker sheaves on the Grassmannian rather than spherical sheaves on the Grassmannian, you get just point mod G-check, just the clean rep G-check category. So there's various. So those are maybe not answering your question. I think the most interesting cases. Then there's ones that appear in number theory in this theory. Like I think probably the most interesting ones are these kind of funky spherical varieties. There's all kinds of funky spherical varieties. So yeah, so there's a list of examples, and the idea is that this is kind of a framework to unify them. And maybe what I should say is that there's a local conjecture, but there's also global conjecture, and there's local global compatibilities. So I was kind of focusing only on the kind of local conjecture about loop spaces. There's also a global conjecture. It's about matching sheaves on Bun-G with sheaves on local systems, and various related structures. So it's kind of a package. I think this field theory is a way of kind of organizing all these into a package of structures. But
I've got another question. So Kapust and Witten use singular monopoles to realize the space of Hecker modifications. For your boundary conditions, does the gauge theory enter explicitly?
Right. So that's a great question. Certainly not from me. I mean, it should, but I don't know how to. That's part of the things that I don't know how to express. I mean, I don't know. Yeah, the A theory for me does not. It's something I don't really understand outside of curves. So, for example, as you say, like to the Hecker modifications, if I'm thinking about, so Kapust and Witten, as you say, to a three-manifold, I'd look at some space of singular solutions of the Book-Milne equation. That's how we'd make sense of the kind of pictures I drew. I don't know how to say that sort of in the language of algebraic geometry. So in the case of Hecker modifications, we somehow can get away. We don't need to. Just can say what a Hecker modification is without knowing about monopoles. But it's unfortunate because the more we understand of the A theory, the better, the more things we can define in the A theory, the richer conjectural, the richer story you get. So, so there are kind of three manifolds you want to evaluate the A theory on. The only three manifolds that I understand are things where you take like a two manifold and cross with a circle, or more interestingly, take a mapping torus of a diffeomorphism in number theory that you want to take that to be the Frobenius. So you have a curve over a finite field and take its Frobenius map. And that's defines a kind of three manifold. So a curve over a finite field appears as a three manifold. And there you can say what the space should be without knowing anything about monopoles. You can just, you get these spaces of Stukas.
Yeah, but there's something I haven't understood here. You're going to the A side, the B side, but even on the A side, I haven't understood. You're taking some variety X on which the group G acts. And what I was saying I'm not understanding is how the monopoles are even appearing there. Because your variety X is somehow separate too. I thought that you just take varieties on which G acts. And how does that I mean, the Hecker modifications live on the three manifold, you're right, but the variety X has nothing to do with this. Isn't that correct?
Yes. Sorry, I guess I misunderstood the question. So
the question's about the boundary conditions So you have this gauge theory in 3 dimensions, and now you've got this external variety X on which the group GLNC acts.
Yes.
I'm not understanding how they're interacting.
Okay, right. Okay, so I mean, yeah, sorry. Yeah, so if you look in Gallardo-Witten's work, you could say, so first of all, they're not looking at the level of the topological field theory, they're looking at the level of the supersymmetric field theory. So here I replace X by its cotangent bundle, and to really get something at the level of a full supersymmetric theory, I need the cotangent bundle to be a hyperkähler. So the kind of maximally supersymmetric boundary conditions that come from hyperkähler actions of G. So what you can write down is this is just on the level of just algebra of supersymmetry, before you try to do any field theories. You can write down a boundary conditions for n equals 4 super Yang-Mills. So here we have the bulk theory has a gauge field, but it also has some scalar fields and some fermions. There's a collection of fields in the supersymmetric theory. And you can write a boundary condition for those where you couple it to a sigma model into a hyperkähler G space. And so you can write down exactly which, so it's sort of going to look like Neumann in some directions and so on. You have to say so you couple, you have a hyperkähler manifold defines a 3D supersymmetric sigma model. So your fields are maps into this M, this cotangent bundle of X, plus some other partners of those. And there's an explicit coupling of those two fields in the bulk. Yeah, so in the physical picture, it's really, X is not really appearing. It's this hyperkähler space that's appearing, this cotangent bundle. So I wasn't assuming anything was hyperkähler because I was only looking at this topological twisted theory. But yeah, so those are not, so I think I won't be able to give you something coherent right now, but there's not very complicated coupling. I mean, this is something you can generally expect. If I have a gauge theory, I have some gauge fields in the bulk, and I ask what kind of boundary conditions I can do. I can always couple gauge fields in the bulk to maps into a G space. And now I have to keep track of a whole bunch of other, superpartner fields. But that's just and the easiest example of this is just 2D gauge theory for a G space. You can couple to quantum mechanics on a Riemannian manifold with a G action. So in other words, on the boundary, you're looking at not maps into X, but maps into X twisted by a G bundle. You have a principal G bundle, and you look at sections of the associated X bundle. And those are your boundary fields. Does that answer more?
Yeah, great, thanks.
Thank you enormously for the very nice talk.